What's going on again, linear algebras? It's Mr. C here. I'm going to do the second video for the section 4.5 note packet, where we're going to discuss the theorem at the bottom of page 1 and then see how it connects to subspaces of R3. The theorem here says that if W is a subspace of a finite dimensional vector space V, then W itself is finite dimensional, okay, because the alternative would be infinite dimensional, in which case W would be larger than the vector space V, and it would no longer be a subspace. Theorem part B says that the dimension of W is less than or equal to the dimension of V. So this means that the subspace W, the only options in terms of the number of basis vectors is that it either has a smaller amount of basis vectors than the vector space V, or it has at most the same number of basis vectors as the vector space V. And part C kind of dovetails on that. It says that the vector space W is equal to the vector space V if and only if the dimensions match. So if W is a subspace of V, and it turns out that both vector spaces have the same number of basis vectors, they're actually going to generate the same space. So in which case, the subspace W is equivalent to the vector space V. They should look no different. So that's all very abstract. So what I'd like to do is just kind of connect some of those results with by examining some subspaces of R3. The first subspace is the origin, which this is kind of like a zero vector space where the set just consists of the zero vector. By definition of dimension, anything consisting of the zero vector only is going to have dimension 0. And if you think about it, namely if you kind of take a trip down memory lane with some geometry facts, the origin is a single point, and we know that the dimension of a single point from geometry is 0. Another subspace of R3 is a line through the origin. A line through the origin is one-dimensional. We probably remember that fact, that a line has one dimension, or is a one-dimensional object. The reason why it's defined as one-dimensional here is because you would only need one basis vector in order to construct this line. So I'm going to draw a vector V which connects to the origin and goes along the line that is going through the origin. You would only need one basis vector to construct a line through the origin. Therefore, it's one-dimensional. The next subspace of R3 is a plane through the origin. Let me ditch this vector V from the line through the origin. And it's not shown up too well in my scan of the note sheet, but in your copy of the note sheet, hopefully you're seeing a shadow of a plane. I'm going to do my best to draw it out on this one. It should be going through the origin. And a plane going through the origin is another subspace of R3. And the reason why it's two-dimensional from a linear algebra standpoint is because it would require two vectors in order for its construction. Two basis vector, that is. I'm going to connect a basis vector to the origin, call that V sub 1, and another basis vector going in a different direction than V1, call that V sub 2. And it would only there would only be two vectors required in order to construct a plane through the origin. Therefore, the plane through the origin is two-dimensional. Of course, another subspace of R3, kind of a freebie here, is R3 itself. Okay, it turns out that a vector space is naturally a subspace of itself. It's kind of a special case where all of the vectors of the subspace are the same as the vectors of the original vector space. But the reason why R3 is three-dimensional, as we saw in the previous video, is because no matter what basis you use for it, all bases will have three vectors involved. All right. So an example of a basis for R3 would be a vector that could lie along the x-axis, v sub 1, not necessarily equal to I, but maybe we have another vector here lying along the y-axis, not necessarily equal to j, and then maybe another vector lying along the z-axis, not necessarily equal to k, which we'll call v sub 3. Heck, they don't even have to be lying along the axes at all in order to be basis vectors, provided that they span R3 and are linearly independent. So that's some of the connection between the theorem and R3. Some other noteworthy items. Notice that each one of these subspaces has finite dimension. Okay, none of these have like a dimension of infinity. All right, they're all finite numbers. For example, the origin is 0-dimensional. That's a finite dimension. The line through the origin is 1-dimensional. That's a finite dimension. The plane through the origin is 2-dimensional. That's finite. And of course, R3 itself is 3-dimensional, and that's a finite dimension. It also turns out that each one of the dimensions of the subspaces here are less than or equal to the dimension of R3. Case in point, the origin's dimension 0 is certainly less than or equal to 3. The line through the origin's dimension 1 is certainly less than or equal to 3. The plane through the origin's dimension 2 is certainly less than or equal to 3. And then, of course, the dimension of R3 is certainly less than or equal to 3. In fact, it's equal to 3. All right, so hopefully I've explained all that enough. In the final video here, we're going to solve a homogeneous linear system and figure out the dimension of the subspace that the solution generates. All right, in the meantime, let me know if you have any questions about this one. Otherwise, I'll catch you in the next video. Thanks for watching.